Alright, so let's talk more about these relationships, and using multiple representations is very important for you to understand. So we're going to talk about the constant rate of change. And the different representations. Okay, so here's your word problem. That's your verbal representation. A worm can travel 13 centimeters in 4 seconds. So the constant rate of change is 13 centimeters per 4 seconds, or 3.25 centimeters per second. And we got that by doing 13 divided by 4. Okay, so 3.25. So 3.25 centimeters per second. That is your unit rate, or your constant rate of change. Okay, algebraically, that's the equation. Algebraically, we have y equals 3.25x, which we got from this, or distance equals 3.25 t. T is your time. Okay, so centimeters is 3.25 per means multiply second. Constant of proportionality, because this is a proportional relationship, if the worm travels 0 centimeters 0 seconds, it's proportional. Okay, so constant of proportionality would be y equals kx. K equals the 3.25. That's where this came from. Okay? All right, numerically, that's where we include the process, not just the table, but the process. 0 seconds, I would say 3.25 times 0, which gives me 0 centimeters. 1 second, it's going to give me 3.25 centimeters. 2 seconds, that's 10, that's 5, and that is 6.5 seconds, centimeters in 2 seconds. If it's 3 seconds, 3 times 5 is 15, 3 times 2 is 6, plus 1 is 7, 3 times 3 is 9. You can also see that we're adding 3.25 each time. So 650 plus 3.25 is 9.75. So generically, for any number, it's going to be 3.25 times that n, which is the generic number, and it's going to give me the distance in centimeters. So if we wanted to make this our variables, our seconds and centimeters, then we would say seconds would equal centimeters, but we'll just put 3.25 in. Okay? All right, let's move that into a table. And the difference between the numeric version and the tabular version is that we're taking out the process and just listing the values. Okay? So in this case, we said 0 seconds was 0 centimeters, 1 second was 3.25 centimeters, 2 seconds was 6.5 centimeters, and 6 seconds, little jump here, 6 seconds, you can double this, or you can say 3.25 times 6. 5 times 6 is 30, carry the 3. 6 times 2 is 12, plus 3 is 15. And 6 times 3 is 18, plus 1 is 19. So it should be 19.5 centimeters. And again, 3.25 in. Now this is a vertical table. A horizontal table is not any different. It does not change the values just because we're writing it vertically instead of horizontally. The values are the same, even the 3.25 in. It's just a matter of the way that you read it. So the labels are very important. Okay? All right, so let's talk about if we graph that. Hopefully by now you're comfortable graphing. So we're going to say, put your labels. And this is going to be time time is always your independent. Okay, and so if that's time, then this is distance. All right. And graphing our points, we had 0, 0. Then we had 1, 3.25, which is going to just be slightly above the 3, about a quarter of a way up. And then we had 2 and 6.5, which is halfway between the 6 and 7. And then we jumped all the way to 6 and 19.5, which I cannot graph. But earlier we did 3 and said that 3 was 9.75. So that's going to be 3/4 of the way between the 9 and the 10. And using your straight edge, you will be able to connect those into a line and just keep the line going all the way up to show that as time increases, the distance also increases. Pictorial is kind of like your models that we did back when we did our equations. So in this case, we know that the constant rate of change is 3.25 centimeters per second. So we're going to say for every 1 second, that snail is going 3.25 centimeters. So in 4 seconds, if we do 3.25 plus 3.25 plus 3.25 plus 3.25, we know 0.25 4 times is a whole, and then 3 times 4 is 3, 6, 9, 12, plus 1 more gives me 13. So the caterpillar travels 13 centimeters in 4 seconds. And that is how we do the constant rate of change in all these different representations.